is the 125th anniversary of the first class of Union College. Hooray. So that means y'all get free supper down where Jorgensen Hall used to be at 5:30 today. For the people that are at Southwestern, I'm sorry, you're not going to be able to take advantage of that. You may not be aware of this, but up until the very early 1970s, Southwestern they weren't accredited to offer baccalaureate degrees, Bachelor of Science, Bachelor of Arts, until 1970. And so up until that time, students at Southwestern actually came to Union College to finish their education. So I have relatives who started at Southwestern, did 2 years there at Southwestern Junior College, and then came to Union College to finish their degree. So it's kind of a Southwestern-ish thing too. Okay, so we are going to pick up talking about momentum. Thanks for visiting, Darla.
Yeah.
Talking about momentum. And so up here in the right-hand corner, I have Newton's second law, the correct Newton's second law, except for you'd have calculus, a derivative if you want to be 100% correct. Force net is equal to change in momentum over change in time. And so just like I did on Wednesday, we can rearrange that to the change in momentum is force net multiplied by change in time. Now, you probably noted I dropped off the vector signs here because I'm working in one dimension. This is really a three-dimension, right? It's a vector property, the change in momentum and the force. But this brings up an important idea. Now, to me, the word is not important. It's the idea that's important. There is a relationship between the net force in an object and the time that net force is applied and its change in momentum. And so, by convention, the force net times time is called the impulse. So impulse, well, if you look at the other side, the equal side, that's equal to change in momentum. I generally just say, what's the change in momentum? And I don't ask, what's the impulse? But impulse is a word that means the net force acted on an object over the time, this is the time it acts for, and it's equal in value to the change in momentum of that object. Now, why is this important? Let's think about things like automobile safety. Back in my dad's day, automobile safety was kind of like an afterthought. I mean, they did things like, it would be much more cool to drive the Model T from the back seat. So they just welded on an extension for the steering wheel and put on extensions for the pedals, and they drove from the back seat of the car. Right? They didn't worry about seatbelts or anything. But people started worrying about individuals dying in car accidents. And so what's the first primary safety thing that was put in vehicles to keep people from flying out of the cars when they get in an accident? Seatbelts. So they put on lap restraints, right? Belts to go over your lap. And that's all fine and good until you get into an accident. But typically you're going to accident, you're moving forward. What direction is your momentum when you're moving forward? By definition, forward. And when you hit something and the car stops quickly, what does Newton's second law say is going to happen to you? You're going to try to keep going forward, but you have that lap belt that keeps your waist from moving forward. So what happens to the rest of your body? It moves forward and you go, whee! And you can make your head hit that dash a lot harder than it would have if you didn't have the seatbelt on. So that's not really a good safety factor right there. So then they said, well, we'd better put, a shoulder strap on there to keep the upper body from flying forward when the waist stops. And so you have now the shoulder strap, a much bigger safety. I mean, you need to have both if you want to actually have the safety there. But it keeps your head from flying forward. I got to tell you, the first call I ever went on as an EMT, my first ambulance call, we had this guy who'd been tweaking for 3 days, and then he fell off a ladder. I don't know why. And he didn't have a license. Why would a tweaker not have a license? Anyway, but he jumped in a car to drive to his mother's house so she could take him to the hospital. And on the way, he fell asleep and hit a tree.
Well, at least he was asleep.
Yes. And he was well out of it. He did not have his shoulder restraint on. And so his head came forward and bounced quite nicely off of the, I don't think he had a seatbelt on either, off of the windshield. And so my job in that call, my brother was the lead, I was the trainee. And my brother said, okay, your job is to just keep blood from going into his eyes. because his nose was just mashed up. It looked like hamburger. And the guy was like, how bad is it? Well, it's not good. Can you tell? Well, you're not going to win any. I told him this. You're not going to win any beauty contests. On my patient care report, I said that we could not identify his nose. Because got away with words on those patient care reports. Anyway, so that's why we have these things. But of course, there are other issues with them. Because if you look at this equation, when the car stops, you have a certain speed in a certain direction, and you have a certain mass, so you have a specific momentum. And after the accident's over, what's your momentum going to be? Zero. I mean, hopefully, unless you're flying off a cliff and it's, Okay, so your momentum is zero, so your change of momentum is going to be whatever you had when the car hit something to zero. And then you're going to have that change of momentum is equal to the net force multiplied by the time over which it acts. So with the early versions of seatbelts, they just bolted those things to the chassis of the car. The seatbelt isn't going anywhere. And so when the car stops, the belt stops, and your body hits those belts. And so the time that you're going to have to stop is going to be really small because those belts aren't stretchy or anything. And so that means the force of those belts would be really large. And of course, you still do have the whiplash action with the, what are you going to do about whiplash when you have the shoulder belt? I don't know. So they added more things for safety. They put in, I haven't taken it apart, but you may have noticed that when you pull on the seatbelt, there's actually some give there, and you have you can pull it forward, and it has a catch. Well, these things are designed to make it so it doesn't stop you as quickly. And the seatbelt is not just bolted to the chassis. It's bolted to kind of like a shock absorber with a spring in there that's bolted to the chassis. So when you get in an accident, that seatbelt is going to expand a little with you. And if it expands a little with you, that's going to elongate the time to stop. It's going to make it a longer time for you to stop. Probably should have said the word elongate. I have to do a distance. Well, if it makes it a longer time to stop, what effect does that have on the force you receive from that seatbelt? It lessens it. So it makes it less damaging. Well, then people got really, really smart. And they started installing little guns in your car, right? Because, if you've ever thought about it, those airbags, they have an explosive in there. And when you get in a crash, if the acceleration is high enough, it triggers it to set off the explosive. And that, was it sodium azide, or I don't know, that explosive then goes boom, and for the steering wheel airbag, it'll shoot out at you. Anybody have any idea how fast it'll shoot out at you? 200 miles an hour or so. So that bag is coming at you really fast. If that bag hits you at 200 miles an hour, it's probably going to hurt. So the bags are designed with big holes in them. So they don't really inflate. They shoot out and they instantly start to deflate. So when you push on it, you're just pushing that air back out of the bag. And so the goal there is to make it a longer time for you to stop, because that bag comes out and it should stop just before your chest. You hit it with your chest, and then and you blow all the air out of it quickly, but longer than it would have been otherwise. Yeah. So all of these things, the goals of all of these safety things I've mentioned so far were to make the time for you to stop a longer time. Because Newton's second law here says that if you can make the time part longer, then the force goes down, less force in you, less damage on you. Now, just a few considerations about the air safety bags. I believe it's federal law. If you are really short, you can go to the dealership and they have to disable your airbag. Why? Because if you're really short, it will be hitting you while it's still coming out, and it can be damaging to you, break ribs and stuff. And so for really short people, you can actually go and have it disabled because it's safer without the airbag. I learned, because my son took driver training last year, when I was a kid, you're supposed to hold the steering wheel like this, right? No longer, because they don't want your thumbs to be over where the airbag is going to deploy, because it'll snap your thumbs. Nobody wants to have their thumbs broken, so you're supposed to have your arms, hands a different position so that your thumbs aren't going to be over where the airbag deploys. So keep that in mind as well. Nobody wants a broken thumb. This picture here, I haven't talked about the picture at all. The picture is a way for us to deal with something like the impulse delivered to a ball when it bounces. Right? The ball bounces. How long is that ball in contact with the table? Just shoot out a random number. Well, not a random number, a number that you think is reasonable. Okay, a tenth of a second? Okay. So a tenth of a second, it's a very short time. It's probably a lot less than that, but it depends on how bad the ball is. The worse the ball, the longer it's in contact. So it's a short time. While it's in contact with the ground, it's probably not going to be a constant force because it was zero force until it hits the ground, and then it's going to build up to its maximum and then drop back down as it rebounds. And so the graph here shows a realistic force profile for something like the ball bouncing. And so the impulse is the force multiplied by the change in time. And you know what? Just like for finding distance traveled from a velocity versus time graph, or work done from a force parallel versus distance graph, we can find the impulse by taking the area that is under this curve. Because the vertical is the force net and the horizontal is the delta t's. You add up all the force net times delta t's, and you get the total impulse. Now, for our calculational purposes, this lavender, lilac, purple, whatever color it is, region is saying, well, you could try to approximate this by saying, well, the average force, or the effective force, as they called it here, is this high, and the time it was in contact was from here to here. So we'll just take the average force multiplied by the time of contact to get us what we think would be the total impulse. That's not the correct way to do it, but it's a way to do it when you don't have all the information, right? You have a graph like this, you're like, oh, I can't add all of that up. Okay, this looks like it's the average, this is the time. And so it's a way to get close. Now, our first of many clicker questions, it turns out. And you can start answering now. What quantity is synonymous with impulse? Only one answer here is correct. Okay, give it about 10 more seconds. All right, see what we got here. Okay, we had 51 people that said change in momentum. I'm not going to ask anyone for the reasoning on this because the best answer I could likely get is the previous slide said it was. That's not going to require a lot of thoughtful reflection, so there's not a lot of point in doing that. Okay, when we are looking at collisions, we're going to look at collisions. You can see I've got some stuff set up here. We're going to live life on the edge and try going to the wireless so I can do that. It's important that we identify a system to work with on a collision. When we work with collisions, we don't look at, a car collision. We don't look at just one car, because for that one car, for that one car, clearly during the collision, it had a net force that wasn't zero. And so momentum clearly isn't conserved for a single car in a collision. So you have to define your system so that you're including the two things that collide. So as an example, I take this ball, I let it drop, it hits the ground, it collides with the ground. The ball clearly changed momentum during that collision, right? there was a net force acting on it for a certain amount of time, giving it an impulse, change. But if I were to take the ball and the thing it hit, the earth, and take that as my system, then for that ball earth system, if there's no moon, no sun, and no stuff like that to worry about, I could say the net force on the system was 0. And then momentum would be conserved. So you want to look at your system and identify your system. So the net force acting on the system is 0. You have internal forces like the force between the ball and the floor, but those are internal to my system if I had to make it the earth and the ball. So this here is an important thing for doing our collision problems. You want to identify your system so the net force in the system is 0. Why is it important to have the net force 0? So momentum is conserved. If the net force is 0, then the change in momentum is 0. So momentum is conserved. So that's the first step you need to do, is to identify, do I have a system where the net force on the system is 0, so momentum is conserved within that system? If momentum is conserved, then we're going to be able to use conservation of momentum as a solving method. Now, one more thing, and I'm not going to belabor this. I'm not going to spend a lot of time on center of mass, but the center of mass is an important principle in physics. The center of mass is a calculation about the average position of the mass. So just like if you were going to say, what's the average grade on an exam? Average grade on the exam, I add up all of the exam scores and divide by the total number of exams, right? So for the average position, I have to do something a little different. I have to do a weighted average. Like it would be like saying, okay, I had 3 isn't right. I had so far 4 exams with 100%. I'm still not done grading the exams. Getting closer. I spent yesterday again grading. So I have 4 exams that are 100%, so I'd have 4 times 100, and let's say I think I have 1 exam at 97, 1 exam at 96, so plus 1 times 97, plus 1 times 96, and on the way down, add all of those together and then divide by the total number. Or to look at an exam problem, do you guys remember the exam problem that had a graph something like this, and it was velocity on this axis and time on this axis, and you had to find the average acceleration? The easiest way to do that problem was to say acceleration average is equal to delta V over delta T is equal to V final, 0, minus V initial, 0, over the total time, 24 seconds minus 0. That was the easiest way to do it. But there are a lot of people who correctly calculated the acceleration for this part, which was 5.0 meters per second squared. The acceleration for this part, nice job, which was 0, and the acceleration for this part, which was minus 2.5 meters per second squared. But then almost every one of the people who did that, when they went to take the average, they did 5 plus 0 minus 2.5. I don't know what they divided by. That doesn't give you the right answer. It doesn't give you the right answer because it was at 5 meters per second squared for 6 seconds. So if you wanted the average from that, you'd have to weight it. 5.0 meters per second squared times 6 seconds plus 0 meters per second squared times 6 seconds plus the minus 2.5 meters per second squared times 12 seconds, because it was 12 seconds on that last part, and then divide by the total weighting factor, so divide by 24 seconds, and then when you did that, it gave you 0. Right, so it's that weighted average that you had to do there if you did the acceleration for each part. Now coming back to this, you're taking the weighted average of position using the mass as your weighting factor. So you're saying I have this much mass in this location, plus this much mass in this location, plus this much mass in this location. You add all of those up and then divide by the total mass, and it tells you the average position of the mass. Why is this concept important for us right now? Because we can take our physics and say that Newton's second law applies to the center of mass of this ball. So if I throw this ball, here, Jordan, I throw the ball to you. So I throw the ball to Jordan. As it goes through the air, the ball went up, the ball went down, and made a nice little parabolic section. Fine and good. Now let's say I take this, I'm not going to throw this to you. It's glass. It would be a bad call. But if I threw this to Jordan, it'd be going through the air like this, right? And then I'm saying, okay, so if I look at this tip, it's going up and down and doing these loops as it goes through, and it's doing a convoluted pattern. But if I look at the center of mass is going to follow the same path that the ball did. Because the center of mass, I can treat as if all the forces acting there, so the net force, mg down, gives me my acceleration of g downward, horizontal velocity of that center mass constant. So if we're doing collision problems, that idea really is nice. You have a problem like this rocket that is separating. The center of mass of the rocket does a nice parabola, right? It's not burning at this point. So it's just doing a nice parabola. And then when it separates, part of it gets blown backward, part of it gets blown forward. The center mass stays in that parabola, and then you can calculate the motion relative to the center mass easily. So it's often useful to work problems in the center of mass reference frame, where you just convert all of your velocities to what they are with respect to the center of mass. Then you have the center mass doing whatever it's doing, and the motion of everything else with respect to it. So that's why center mass comes here. There's some interesting things about center mass. I told you guys I'm totally a sports junkie. Olympics, I watch like every competition I can. And so when you're watching things like the high jump, the history of the high jump is built by a, shall we say, self-described lazy jumper who just wanted to find an easier, funny way to jump. And so I'll call him Richard Fosbury because I am rather opposed to the nickname he goes by. When he was in high school, he was on the track team because he was tall and fast and whatnot. And they had him do the high jump. And so doing the high jump back then, you would run up and you would do a scissor kick over it. So you jump up and kick that one leg up and kick the other. And in so doing, your center of mass has to pass fairly high over the bar because when you lift your leg, of course, your center mass comes up and your center mass is probably somewhere around your navel as you're going over the bar. Well, Fosbury was goofing around in high school and he just kind of ran and jumped backward over it. And to his amazement, he found that he could do higher heights. And so he started doing that in competition, and he became like the best high jumper in the world because he developed a new method. Well, he got to college, and his college coach said, okay, we know you're a really good jumper, but you've got really horrible technique. We've got to get rid of that and get you back to doing it the right way with the scissor kick. And so he tried to do it the right way, and his heights dropped off again. And finally, the coach relented. He went back to doing what we call the Fosbury flop. And now everybody does it. Why is it advantageous? Now, there are some mechanical things, I think, that make it advantageous. But from a physics standpoint, the one that I care about the most is when you're going over the bar, you get to that bar. So you have, here's the bar, and you get your head over. So your head's here, your body's like that. Well, once your head's over, you want to drop that head, get your shoulders over, and drop those arms down. So next thing, you're like this with your arms down here, and your head down here, and your legs down there. Well, when you're in a shape like that, your center of mass is going to be somewhere like here. And then as soon as you get your butt over, of course, when your butt's over the bar, you put your legs like this. And of course, your center mass at this point is going to be somewhere down around here. And so doing a high jump with the contortions that Dick Fosbury came up with, or doing the pole vault, you're doing it the other direction, but you're obviously once again contorting your body to try to get your center mass down, you can actually clear a height that's about 6 inches above the height that your center mass goes. So it's a way of elevating the height you can clear for the same amount of jumping ability. Any questions? And no, I can't high jump in case there's anyone like, can you show us? No, I cannot. Conservation of momentum. This picture is just to illustrate a lot of things where conservation of momentum is used. In particle physics, like over there at CERN where they are using the not superconducting supercollider, that was Texas. The Large Hadron Collider, conservation of momentum during the collisions between the things they're banging on each other is an important part of the calculations that they do to figure out what they found. So, this is a picture illustrating you have a macroscopic target, piece of, I don't know, let's say a piece of cadmium, I don't care. And you have a particle that hits it over there at the Large Hadron Collider. I don't think they're shooting electrons. That's more what they're doing over at Stanford. But you hit it with a particle, and that particle will actually interact with the nucleus and cause a quark to rebound, and they're calculating conservation of momentum between, in this case, the electron and the quark in the nucleus as part of their calculations. And over here on the right is something that's much more rubber meets the road. Yeah. Of analyzing what actually happened in a collision. If you look at this collision, you're like, well, I can't tell what happened because clearly this vehicle is different than this vehicle. There's no car that's going to have it, And, you've got all kinds of skid marks. And so, it's more than I would have to see, like at least how many vehicles were involved to make some sense out of it. But they measured carefully all of those lengths, and you have, groups that specialize in going to court and saying, well, our reconstruction of the accident based on the skid marks and the masses of the vehicles and so on says this happened, it was going this fast, and it hit this hard. So that's a very practical application of this. Now we have two fundamental types of collisions. And I'm going to have Jonathan come on up and help me here. This is where hopefully everything stays on the line. We go from wired to wireless. So far, so good, right, everybody? Okay, so now Jonathan is going to, are they sticking or not? No, not sticking. Okay, so we have two carts here, and there are magnets in the carts that make them repel. So as long as you don't have them hit too hard, they will repel off of each other. And we're going to look at what happens during a collision like this. So go ahead and start. Okay, now on the graph, you can see on the top is the momentum, and there are three lines for momentum. The momentum of cart 1, you can see the momentum from him, the one he pushed, the momentum of the second cart, and then there's the total momentum adding the two together. Now, if you look at the graph zoomed out like this, what do you note about the total momentum in this upper graph? What's the bluish looking line doing? Stays relatively the same, but it is decreasing. Momentum is dropping. If we look at the lower graph is looking at kinetic energy, and that's more clear. The kinetic energy is dropping over time. Why is it dropping over time? Friction, right? Friction is doing a negative work, lowering the kinetic energy in this case. Now, for your analysis, you want to only analyze what's going on during the collision. So I choose about 3 data points before to about 3 data points afterward. So I rescale it. So I'm just looking at what was happening during the collision. Come on, there we go. And so I can say, well, during the collision, what happened to the kinetic energy? The kinetic energy started, missed again. Okay, kinetic energy started here at, 0.22 or something, 0.21. And it ends over here at like 0.20, or there's a 0 there, 0.02 something. The kinetic energy dropped just a small amount, but we can understand that that was because there was a certain amount of friction. So I would look at this and say, well, given the context of the slope of the line before the collision, I'd say that kinetic energy stayed about the same. It was just friction that was changing it because we did have an external force. And if I look at the momentum, how the total momentum change, once again, within the slope it had beforehand, it appears to have just stayed constant. So this collision where the two actually didn't physically touch, but I just had, they came close, magnetic fields caused repulsion, they went apart. The total kinetic energy, what's the term we use if it didn't change? It was conserved. So the total kinetic energy was conserved and the momentum was conserved. Momentum was conserved, well, not quite because we did have friction, but it was approximately conserved because we had no external net force except for, of course, that friction. The kinetic energy was conserved because of the way the collision went. Not all collisions have that property. So we're going to show the other kind. This kind of collision is called an elastic collision. Elastic collisions are collisions where the kinetic energy is conserved. Not all collisions have that, but the ones we call elastic do. So now let's do another experiment. Did you turn around? So now he's turned a card around. Now it won't have magnets to repel, but they have Velcro on them. Ooh, invented by NASA, right? Either that or it came from alien technology, depending on which conspiracy theory you want to believe. And so the Velcro is going to hold them together. And so we're going to basically repeat the experiment. So you ready? Okay, go ahead. All right. Now, when you're doing this, this is what we're doing in lab next week. When you're doing this, you always need to make sure you find where the collision occurred. You might notice that my timing for when I started the experiment was such that you didn't see the initial push. If you saw the initial push, you would have had a very dramatic thing at the very beginning. And some students say, oh, there's my collision. No. You need to be more careful and make sure you identify the collision correctly. So in this case, my collision occurred, wrong place, right there at about 2 seconds. So zooming it out just like I did before. Now trying to move this, there we go. There is a way to make these lines darker, but in my 10 minutes I had before class setting up, I couldn't figure out how. But if you look here, the total kinetic energy, would you say that was conserved? No, it definitely took a drop. So in the case where they stuck together, the kinetic energy was not conserved, it dropped. What about the total momentum? Up here in the upper one, that blue line. It was conserved. The total momentum should always be conserved in our collisions if there was no friction and I have my system defined right. But the kinetic energy depends on the type of collision. So if it is an elastic collision, kinetic energy is conserved. That's the name we have for it. An inelastic collision means a collision where kinetic energy was not conserved. And for our purposes, we're just a general physics class here. We will just pretend that there are only two types of collisions. Completely inelastic. Oh, what did I? Okay. Completely inelastic collisions where they stick together, such as they did right here, and elastic collisions where they bounce off each other and the kinetic energy is conserved. So I will very often, like textbooks, say elastic collision, and what I mean is completely elastic, that they stuck together. So when you hear elastic collision, your brain should click to they stuck together, so the final velocity of one was equal to the final velocity of two. Excuse me? Did I say elastic when I meant inelastic? Yes. Okay, when I say inelastic, I mean they stuck together, so final velocity is equal to initial velocity. I would joke about senility, but people might take it seriously. Don't think I'm going senile. So in that case, the kinetic energy changes. This picture here shows your system with the net force acting on the system of 0. And it says kinetic energy internal is mv squared. What's the equation for kinetic energy? 1/2 mv squared. So why does that say mv squared? Because there are two masses that are both m and both moving at speed v. Well, at speed v. One has velocity plus v, one has velocity minus v, but they're both at speed v. And so this one has kinetic energy 1 equals 1/2 m times v squared. This one has kinetic energy 2 equals 1/2 m times minus v quantity squared. You add those two together. You don't get 0 because that minus sign is inside the square. Instead, you get a total of mv squared. So that's where it came from. Because you look at it first and you think, he made a mistake. Or the textbook in this case. The total momentum here, mass 1, v1. Well, the v1, velocity 1 was in the positive direction. Mass 2, v2, velocity 2 was in the negative direction. So those add up to total momentum of 0 initially. In the final case, since it's inelastic, your final momentum has to be the same as the initial, which means it's going to be 0. And if they stuck together and the final momentum is 0, what does that tell you about the final speed? 0, right. So it's very simple for this case. So if I had had Jonathan do the case where the two carts were coming together at the same speed, stuck together, they should have just stopped. Now, in the experiment that he did, what happened to the speed when they collided? It decreased, and in fact, it just dropped in half because I had the same masses and one was stationary. If they're equal masses, it's very simple to figure out what's going to happen. If it's elastic and they're equal masses, let me change that. If it's elastic and they're equal masses, they just exchange velocities. So you see one stops and the other one starts with that. If I have them both moving, they still just exchange velocities. So if they have the same mass, it turns out the outcomes are real simple. But if they're not the same mass, so here I'm going to have a heavier one hit a lighter one. Now they're both moving afterwards. And the lighter one went off faster than the heavier one was moving initially. Now if I have the lighter one hit the heavier one, what do you think is going to happen?
Slower.
Which one's moving slower?
The
The heavier one's moving forward. And what does the lighter one do? It's going to bounce back. So when you have different masses, it's more complicated. So we're going to have to learn how to solve these kinds of problems, whether they're an elastic or an inelastic collision. These were inelastic. So in solving inelastic collisions, you have get your momentum initial and your momentum final and set them equal. So if I have two objects, and by the way, we're only going to do one-dimensional collisions in this class. Two-dimensional collisions don't involve anything really that much more complicated, but it's more math, and especially if it's an elastic collision, it does get a little more difficult. So mass 1 initial, V1 initial, mass 1 initial. Mass 1 isn't changing. It's only the speed that's changing. Mass 1 V1 initial plus mass 2 V2 initial equals mass 1 V1 final plus mass 2 V2 final. So you have, that's your first condition for the inelastic collision. Now I'm going to rearrange this in a way that may seem to be no more beneficial, but you'll see when I get to elastic a benefit. So I'm going to move the mass 1s to the left side and the mass 2s to the right side. So that means on the left side, I'm going to be left with mass 1 V1 initial minus mass 1 V1 final equals mass 2 V2 final minus mass 2 V2 initial. And you might say, I don't think he's done anything to benefit himself. Well, I can at least factor out an M. So I have M1 times V1 initial minus V1 final equals M2 times V2 final minus V2 initial. Now, it is important that you've paid attention enough to see that on one side I have initial minus final. On the other side I have final minus initial, right? Because I subtracting things across. Don't blow your head off now. The second condition for an inelastic collision, a completely inelastic collision, is that V1 final equals V2 final. So you have those two relations that you combine to solve your problem. So I can take these two equations. I have to know two speeds, and then I can find the two other speeds, or two velocities. If I can find the two other velocities. Remember, we're doing it one-dimensionally. If you were doing it two-dimensionally, you would have four unknowns, and you'd have to know, excuse me, not four unknowns, you'd have eight. You'd have to know four things. You have six things to get the others. So it gets more complicated in terms of what you need to know. That's why we're only doing one-dimensional. So with those two equations, with four unknowns, I have to know two speeds. Usually we give you the two initial speeds. But as we'll see in the problem that we won't have time to complete, I'm going to give you a different set and work on how we think our ways through. So that's how we work with inelastic collisions. Elastic collisions, well, then we have kinetic energy conserved. So we're going to have two conditions. Number one for our condition will still be momentum initial is equal to momentum final, or mass 1 times V1 initial minus V1 final equals mass 2 times V2 final minus V2 initial. That's still our first condition. But our second condition, kinetic energy initial equals kinetic energy final, or 1/2 m1 v1 initial squared plus 1/2 m2 v2 initial squared equals 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared. Now you look at this, and any reasonable person says, crud. Because now we have these squares everywhere. That's not nearly as easy. Well, I'm going to go through a little mathematical rearrangement to make it easy. It turns out this is easy. Aren't you glad? So what I'm going to do is first, very obviously, multiply everything by 2. I don't need to have a 1/2 with every term. And then I'm going to rearrange just like I did before. So I have M1 times stuff, M2 times stuff. So I'm going to move terms across. So I have M1 V1 initial squared minus M1 V1 final squared equals M2 V2 final squared minus M2 V2 initial squared. And as before, I'm going to factor out the M1 and M2. And I imagine people are still looking at this and saying, I don't see that you've really simplified it. It still looks like it's going to be a doozy. Well, we do one more step before you can see the benefit. We're going to complete the square. Not really. We're going to take this and break the V1 initial squared minus V1 final squared up into two things. V1 initial minus V1 final times V1 initial plus V1 final. Right, if I take the two terms of parentheses and multiply them through, or as I've heard people say since I came here to Nebraska, FOIL it, you see that, honest to goodness, nowhere in my education did FOIL ever come up. We just learned multiply. Yeah.
I learned it FOIL. I learned it FOIL.
Yeah. We just learned multiply. That's the way we were taught. Anyway, but if you do this, you'll notice you have V1 initial times V1 initial squared. You have minus V1 final times plus V1 final, so minus V1 final squared. And then the cross terms, V1 initial times positive V1 final, V1 initial times negative V1 final, those add out to 0. So that's equivalent. Other side, M2, V2 final squared. Whoops, I was trying to V2 final minus V2 initial, V2 final plus V2 initial. And once again, most reasonable people would say, okay, Richard, you've made it more complicated. Congratulations. Can we end class now? But there's one more step to make life easier. This red equation up here. I'm just going to divide the left-hand side by the left-hand side from that red equation. But what I do to one side, I have to do to the other. So I can divide the right-hand side by the right-hand side of the momentum conservation equation. And now we have a simple equation. Because you see, those cancel out. And those cancel out. And I'm left with my conservation of kinetic energy equation says V1 initial plus V1 final equals V2 initial plus V2 final. So if you have conservation of kinetic energy, that equation is going to be true. It's still not as simple as having V1 final equals V2 final. But it's not as complicated as having squares you have to do in your work. So now on the test, I'm not going to give you this equation. Right? I'm not going to give you that equation because it's a special case situation. It's a calculation that starts with the general equations of kinetic energy and momentum. But you'll find life a lot easier if you remember that you can work your way very quickly from conservation of kinetic energy for an elastic collision and elastic collision gives you that the sum of the velocity initial plus velocity final 1 is the sum of the velocity initial plus velocity final of 2. It's actually not supposed to be our last clicker question, but it's probably going to be given we have 2 minutes left. In which case is momentum conserved? Okay, let's go with our answers here. We had 38, 0, 19, 0. Because I only have 1 minute left, I was going to have a lot of discussion on this question, the next question, and the next question after that. Clearly we won't. I'll go to the answer. The answer was in both. Momentum is conserved under what condition? When the force net on my system equals 0. And so we're going to find a system so the net force in the system is 0 for our collisions, and then it will be conserved in all of the collisions. 38 people said only in elastic collisions. What were they thinking? They weren't thinking completely wrong. They were thinking I'd ask kinetic energy instead of momentum. So you have to make sure you're paying attention on which one is which for elastic and inelastic. All right. Have a great weekend. Hope you enjoy the celebration of 125 years.